He kōna e purangi tēnei nā te reo irirangi o Aotearoa.
Yeah, so it burst, and now it's falling. So it got as high as 34 kilometers. And we see sort of like the typical bulge, typical ozone layer, which peaked around 22 kilometers. And this is overall kind of normal looking ozone layer. Sometimes you might see notches in it or divots of ozone poor air, like we've seen that with smoke before from the bushfires. But this is just a good looking profile.
I don't know when I would have learned about the ozone layer, but I think everybody knows about the ozone layer. It's kind of cool to be standing in front of a graph that is like, oh yeah, there it is.
Exactly.
Kia ora, nau mai hara mai ki te ao hurahanga. Hello and welcome to Our Changing World. Ko Concannon tēnei. Is this peak nerd? To be excited over an ozone graph? Maybe. But I feel a bit invested because these results are being transmitted back from a balloon that I watched launch about 2 hours before. A balloon that travelled up through the troposphere, the lowest area of Earth's atmosphere, and into the stratosphere, which is about 15 to 50 kilometres above us. And where you find the ozone layer.
The so-called Antarctic ozone hole is being precisely measured over the next couple of days by a team of New Zealand scientists.
Mrs. Nichols says the man-made chlorofluorocarbons have eaten away the layer to half its normal thickness. The edge of the hole has reached a point halfway between Antarctica and the south of the South Island.
The chemicals are used in thousands of products, from the freezer at the cafeteria to its takeout containers to the foam in your office chair.
It's being called an unprecedented display of international cooperation to protect the world's environment. The Montreal Protocol, signed today, aims at stopping the deterioration of the ozone layer in the atmosphere.
We're talking about human safety, human life, and ultimately, possibly, the continuation of human life on planet Earth.
Almost 40 years on from when the Antarctic ozone hole was first reported, and 35 years since the Montreal Protocol to ban CFCs came into effect, what's going on with the ozone hole? How does it form? How do we measure it? And having solved the CFC problem, why are we still monitoring ozone so closely? Spanners, paradise ducks, birdsong and cows might not be the first sounds that come to mind when someone says atmospheric composition measurements. But that is the backing track to scientists' work at NIWA's Atmospheric Research Station, just outside the small village of Lauder in Central Otago. Atmospheric scientist Dr. Ben Liley is beside me as the balloon that will carry the ozone detector up into the stratosphere is getting filled with hydrogen gas.
We're filling up the balloon at the moment. It's just tied off to a weight so that when it just lifts the weight off the ground, they'll know that they've got the right amount of buoyancy in the balloon. Then they tie the balloon off and disconnect the weight and connect on the package, and it then has enough buoyancy to rise at about 6 metres per second. It will do that for 2 hours until it reaches about 30 to 35 kilometres altitude, going up to an area where the 100th of the pressure there is at the surface. The balloon will increase in volume. When it reaches the limit, it pops and it comes down on a parachute.
The package to be attached to the balloon is the ozone sonde, the device that measures the ozone in the air as the balloon floats upwards through the atmosphere. The weight begins to hover above the ground. The package is attached, the weight released, and then the balloon is let go to float up into the bright blue sky of this pristine Central Otago spring day. Very quickly, this 1.5 metre diameter balloon is already so small. So you'll be picking up data straight away now?
Yeah, it's measuring the profile of pressure, temperature, humidity and the ozone. Now, it won't be measuring much ozone at the moment because there's very little in the troposphere, especially here in a very clean site. If we were launching the same balloon in a polluted city, you would measure quite a lot more ozone because ozone there is a product of photochemical smog. But carry on down and
coffee time.
Yep, coffee and some bickies. Gotta stay appropriately caffeinated when you're figuring out the chemical composition of the atmosphere. Afterwards, Coffee Time announcer, chief balloon wrangler, and atmospheric scientist Dr. Richard Curl brings me in to see how the balloon is doing. We can't see it in the sky anymore, but the antennae on site are picking up the live data it's sending back.
So this is where the balloon has gone so far. So far it's at 13.5 kilometers and it's gone north only about 10 kilometers. So there hasn't been too much wind. Look at what the ozone's doing. It should start to increase and kind of reach the ozone layer here. It's just at the bottom of it, kind of at the tropopause roughly, the separation between the troposphere and the stratosphere. So we should see this start to increase.
As Ben said, while it floats up, it's taking measurements of the teeny amounts of ozone in the pristine Central Otago troposphere. But what they're really interested in is what happens next.
Our main interest here is measuring the ozone in the stratosphere, like the ozone layer itself, where the bulk of that ozone is. And that's where we start to look at these long-term trends. And they're very small trends on the order of a few percent per decade. So that's why you really need these sensitive measurements, kind of highly, quality controlled, so that you can pull out that small signal over the larger noise of seasonal differences and effects from bushfires or volcanoes. It ends up being pretty complicated measurement to try to get down to that small signal, but it is possible.
The thing about the balloon, so you have other ways of measuring ozone here at Lauder Atmospheric Research Station, but the thing about the balloon is that it's actually floating up through the stratosphere. It is sampling the actual ozone.
Yeah, all of the other instruments that we have for measuring ozone are all remote sensing, so it's all inference of how much ozone there is, whereas the ozone sonde itself, it's chemically tasting the ozone where it is. We can't control where it goes, so it'll just go upwards, but it'll get pushed by the winds. And so it won't be necessarily a pencil beam measurement straight up over Lauder. It'll go wherever the balloon has gone.
The ozone sonde itself is composed of a little pump that pushes samples of air through a chemical solution. This solution reacts in the presence of ozone molecules, creating a tiny electrical current that's then detected. It's packaged up with a little heater in a box of biodegradable foam insulation, because it gets very cold in the stratosphere. A little sign is taped to the outside, explaining it's a monitoring device with NIWA's number. They get about 20% of them back. Most go out to the ocean. Because you don't get a second chance once the balloon flies away, and each kit is about $1,500, there's a lot of testing that happens in advance.
Our hands are kind of washed of this. Like, we've done all the checks we can on the instrument beforehand, but what we can do in the meantime is go make a total column ozone measurement with the Dobson spectrophotometer that we have up the hill. And the importance is that it'll be a measurement that's contemporary with the balloon, with what the balloon is measuring. Because the balloon is not going to actually measure all of the ozone. It measures in its path that it's going to, but it also is only going to measure to 32 kilometers, whereas there's still ozone above that.
The Dobson spectrophotometer is up on a little hill beside the office space. A shiny metal dome structure on a slab of concrete that looks kind of like a mini telescope setup. Around it is a robust-looking fence to keep the locals out.
So we're inside a working farm, and there's livestock that grazes through here to just keep down the grass for fire risk. So that's why you gotta watch where you're stepping.
Yeah, I can see a few cow paths around, all right. It's an interesting lab setup.
Oh yeah. Yeah, well there's some up the hill there. So this is gonna be another loud place.
Oh, loud and warm. Both loud and warm are down to the heat pump. Richard flicks it off for now.
What we'll do is we'll open up the dome and we'll get the sun director periscope out, plop it onto the instrument, and we can start a measurement.
The middle section of the roof of the dome slides back over our heads and the sunlight pours in.
So it's a clear sky and we'll do direct sun, and so we'll start that measurement. So it'll automatically, based on the time, it'll turn itself so that it's pointed directly towards the sun.
The Dobson spectrophotometer works by reading the amount of UV light of two wavelengths that it detects. One is absorbed strongly by ozone, so by looking at the difference of the light getting through, the spectrophotometer can estimate the total amount of ozone between itself, here on the ground in Central Otago, and the sun. It's called a total column measurement, which is given in Dobson units, the same Dobson who invented the spectrophotometer.
You can think of it as a thickness of ozone. So if all of that ozone in that column were all compressed down to surface temperature and pressure, it would be a layer that would be a few millimeters thick. And so 300 Dobson units ends up being 3 millimeters thick. So over Lauder, ozone can get as high as 450 Dobson units, possibly 500 Dobson units. So that would be 5 millimeters thick. And it would only get as low as 250 or so. So down to between like 2.5 millimeters up to 4.5 millimeters. It seems like a very small difference, but that is the range of ozone that we measure here over the course of the year.
And for comparison, the worst lows of, we call it an ozone hole, but it's not really a complete hole of ozone, it's just a depletion of ozone. In the 90s, what kind of Dobson units would that have been over Antarctica?
Down to 100, something like that. I don't know what the absolute minimum value is, but it was never zero. And about 100 or so is a pretty low number. The definition of the ozone hole is anything that's below 220. So there's going to be a ring kind of drawn where that 220 line is, a contour. And so everything inside that is technically the ozone hole. So right now it's below that. And so there's parts that are below. Here it gets as low as 250, but the average is more like 300. And no, we never get the ozone hole over our latitudes, over our mid-latitudes. Those are some kind of historical misconceptions.
And luckily, you can also take a reading of ozone using sunlight that's reflected off something, like the moon.
That's one way that you can make measurements with the Dobson instrument in Antarctica. Like where you have 3 months of total darkness, you at least still have the moon. And so it's one way that you could use the Dobson, that we do use the Dobson down at Arrival Heights, which we have sister instruments to a lot of the hardware that we have here running down at Arrival Heights and at Scott Base. So this measurement's been completed, and that is as good as we could imagine of it just being flat. And that's because we're kind of near solar noon, and also there's no clouds in the sky. You might see little kind of up-down blips otherwise, but this is very good. And here the value that it gave us is, if I can see on the screen here, 346 Dobson units, which is pretty typical for this time of year. So what we can do is we can save this, and then we'll just do a zenith measurement. And so the reason is this first measurement was pointing at the sun, but now we'll close the dome and do the same measurement just looking at diffuse skylight straight up, because this instrument runs automatically throughout the day. So a technician has to come in here to do the direct measurement, but it'll do the zenith ones all the time over weekends and holidays and things like that. So what you do is you compare the direct, which is a better measurement, with the zenith, which should give you about the same amount. And so it's that kind of inter-comparison. Yeah, so as much as our instruments are very kind of high-tech, a lot of the problems that we have are low-tech. And there'll be birds coming in, or it'll be leaks, like leaks in roofs. All of our instruments, they all like to look at the sky, of course. And so whenever you have a window, like a skylight, it's going to leak. And it's these kinds of concerns that we always have to end up dealing with.
You've pointed to the ceiling when you said birds, and there are some pointy sticks and
there's some little bird spikes, and there's kind of like I don't know what it would be, chicken wire, like a variety of mesh. And up the hill we have magpie decoys, as well as we have hanging streamers and fragments of old CDs and DVDs stacked as reflectors. And there's places that have this kind of like sticky stuff that's also supposed to be a bird deterrent. I think we've tried almost everything, and in a way, nothing really works. But once you have a combination of things, you hopefully deter them so they don't start coming in and making nests.
Just little notes on the data. Bird, question mark.
Oh, exactly. Well, some are vain as well. Like magpies, they like to go hang out on top of the mirrors for some of the all-sky cameras, kind of watch themselves, and so you'll see them sometimes in your data stream.
They're part of the Network for the Detection of Atmospheric Composition Change, the NDAC. The data collected in Lauder gets fed back into the network for scientists around the world to be able to access and use. We leave the instrument to continue taking its measurements and step back outside to the bright spring day and the collection of buildings, equipment and antennae scattered around outside. There's a NIWA meteorological station beside the Dobson. There are receivers to pick up data from passing satellites. There are instruments to measure CFCs, carbon dioxide and water vapour in the atmosphere, and to detect UV light. They've also got some stuff here that belongs to others. A Building Research New Zealand hut, kitted out with sensors in the walls to measure wear and tear, and a Spanish astronomical telescope with an eye out for big cosmic events. Because as well as having the infrastructure and staff, they've also just got a really good spot.
The main purpose behind this place, I think, is because it is a unpolluted, clean atmosphere that is the example of background conditions. And since we're mid-latitudes, we're exactly at 45 south, so halfway between the equator and the South Pole. We're kind of like what the northern hemisphere would be like if there was no people there, if they didn't have the just constant load of background pollution. So that's why some of the differences that we see here with UV radiation and things like that. The big reason why the air is so clean here is because you can imagine air coming over the Southern Ocean and having been processed by the winds, and then all of a sudden it hits the west coast, and there's 6 meters of rainfall just 100 kilometers west of here, and then we're in this rain shadow of the Southern Alps, so we get only maybe 30 centimeters of rainfall, between 30 and 40, something like that, but certainly not 6 meters, right? And so that 6 meters washes out any aerosol or particulate that's in there, and we get what's left over, which is very clean air.
When it was first set up, Lauder was focused on researching aurora, so looking at the upper atmosphere. Then when the ozone hole was discovered, its focus shifted to the stratosphere and measuring that.
We're known as a bit of an ozone super site because within that NDAC network, there's 5 recognized techniques for measuring ozone profiles.
And Lauder has all 5.
Correct. The only place in the world that has all 5. And so in a way, it's a bit of a Rosetta Stone for other sites that have only 1 or 2 or 3 of these things, because they each behave a bit differently. Ideally, like, they'd all tell you the same answer, but it's kind of like having 5 clocks on the wall and they're all a little bit different. And so now what's the time? Like, you can average them out. Is that a better way of thinking of what time it is right now? The problem is that all the techniques, even though you're measuring ozone, they're all a little bit different.
On top of these, ozone can also be measured by satellites. But somewhere like Lauder, looking up from below as the satellite looks down, can help with ground truthing the data. Having all these measurements helps them identify those small percentage trend shifts across time. Because the story of ozone is not a simple one. Yes, it's affected by CFCs, but by other things too. So let's get into the chemistry a little bit. Ozone is a molecule of oxygen gas with an extra oxygen atom added on. 3 oxygen atoms. It's formed by UV light, but also UV light causes it to break apart. So there's this ozone-oxygen cycle happening in that stratosphere that absorbs all UVC and most UVB light. And that's how it protects us from these high-energy versions of UV. There are different things that can mess with this cycle. And one of those is if there are chlorine atoms up in the stratosphere. And chlorine is one of the ingredients in, yes, you guessed it, CFCs. To get into the chemistry of how the ozone hole forms, I caught up with Dr. Olaf Morgenstern. Now working in Germany, when I spoke to Olaf, he was working in the climate modelling team at NIWA's Greta Point office in Wellington. He talks me through a year in the life of the ozone hole in Antarctica.
The sun goes below the horizon, it's winter over the Antarctic, then the polar vortex forms, so that's a system of strong circular winds, and the air mass in the center of that is somewhat isolated from the rest of the world. It gets very cold. So that's the season when the polar stratospheric clouds form. So this means water and also nitric acid condense into particles, and these particles then they activate chlorine. That means, well, there's a lot of chlorine up there, and in fact there is about 5 to 6 times more chlorine in the stratosphere than before humans entered the scene. So that chlorine is in what we call reservoir forms, and then when the PSCs form, it turns into activated forms.
So we've got our ingredients. A strong winter polar vortex that makes it extremely cold in the stratosphere above the southern pole, about minus 80 degrees. This results in PSC formation, polar stratospheric clouds, which activates the chlorine that's made its way up there in the CFC molecules. There's just one last thing needed to trigger ozone destruction: sunlight. As the sun rises in Antarctica, the activated chlorine starts to break down the ozone.
And so that happens, every year pretty much. When the sun comes up, the ozone hole forms. That's what we expect to see.
And the chlorine that you mentioned, and you said it's 5 or 6 times greater than when humans came on the scene. So that is what we have put up into the atmosphere previously in the form of CFCs.
CFCs and a few other things that we have, emitted. So CFCs were in fact invented in the 1930s by the same person who put lead into petrol. So we have to thank him for that. But anyway.
Thomas Midgley, right?
That's right. Yeah, and they were good. They were perfect. They don't react with hardly anything. Very stable, very nice compounds, very good to handle.
And this was helpful for their role as refrigerants. And then they were used in air conditioning units and aerosol cans. But we later found out they do react.
When they get lofted into the stratosphere to 30 kilometers or more of altitude, then the UV radiation becomes strong enough. So the chemistry becomes such that they do react and disappear. But because the air is so thin up there that every year only a small fraction of the CFC loading in the stratosphere will be affected by that, which means their lifetimes are measured in several to many decades. So somewhere between 50 and 100 years or maybe a bit more, that's typically the lifetime. The peak loading of stratospheric chlorine was reached in 1997. So this was a couple of years after the Montreal Protocol took effect in 1987. Since then, they have been on a slow decline, which is dictated by their long lifetime. We might have lost something like 15% or so since the peak. So it's still elevated and will remain so for quite some time to come.
When you say quite some time, do we have any idea of how much longer?
So we don't need to get down to the pre-industrial level before the ozone hole to disappear. It would be sufficient to get... So at the peak we had about 3.5 parts per billion, so 3.5 molecules per billion of molecules of chlorine. Now we might have about 3.1 or thereabouts. And we have to get down to about 2 for the ozone hole to disappear. So the natural back one would be about 0.5. So it's not that far away, but it still will take some time. Predictions are maybe 2060, roughly maybe in the 2060s, the ozone hole will become more rare. And that also depends not just on the chlorine loading, but also on the other things that we're also emitting, such as CO2, carbon dioxide, methane, nitrous oxide. They all play a role in the stratosphere.
This is where things can get complicated for modelers like Olaf, because changes in the chemistry of the stratosphere air could impact ozone formation or depletion. Plus, every year the ozone hole is slightly different because each winter is slightly different. On top of that, there are external events that can have an effect.
In 2020, I think, we had these very large Australian bushfires. So they are a bit similar to a volcanic eruption, namely they get very hot, and then you get these what's called in jargon, pyrocumulonimbus clouds. So these are very hot clouds driven by, the fires essentially, that get lofted into the stratosphere. They provide surfaces for chlorine activation, and in fact they also deplete ozone.
And the Hunga Tonga Hunga Ha'apai eruption also altered the makeup of the stratosphere by increasing the water vapor levels. There's this very simplified story about the ozone hole, which is the one that I knew. We didn't know anything about CFCs, we figured it out. The world came together to make this decision to ban this harmful thing. We did it. Sure, the ozone hole still pops up each spring, but it's on the way out. And this is kind of true, but some analysis of ozone measurement published by researchers at the University of Otago in November 2023 say it's more nuanced than that, and that the ozone hole could be getting worse in some parts of the stratosphere. We have to keep monitoring, says Olaf, to catch those illegally using CFCs, to be vigilant about anything new we create that gets to the stratosphere, and because things keep changing.
There are new developments such as an increase in space traffic, maybe even space tourism. You know, in the future we might be launching more rockets into space, and New Zealand is a player in that field. And depending on which rocket fuel we use, there can be effects on ozone. They are maybe somewhat exotic threats to the ozone layer, but they need to be considered. And for that, as part of the Montreal Protocol, there is a process known as the ozone assessments. Every 4 years, a new volume, a book is being written to keep up on the state of science and advise policymakers to make sure that we keep protecting the ozone layer. It's less high profile now than it used to be, still quite important that we maintain this.
Thanks to Dr. Ben Liley and Dr. Richard Curl of NIWA, and to Dr. Olaf Morgenstern. This episode was produced by me with help from Ellen Rikers and Liz Garton. Sound engineering was by William Saunders, and it was recorded with the help of Otago Access Radio. Te nakwe I whakarongomai. Thanks so much for listening. I'm Claire Concannon. Have a great week. Kia pai, te wiki.